Okay, we're into the last chapter here. Start talking about nuclear chemistry. And we talked about some different types of particles that we sometimes see in nuclear chemistry. So we have our alpha particles, which is a 4 and a 2. Remember again, mass number up on top, which is our number of protons plus our number of neutrons, and atomic number on the bottom, which is our number of protons coming from the periodic table. Also, again, you could use helium as a symbol for that. We have beta particles, and that's the beta symbol. Also, you could use the electron symbol for it. We have positron, which is kind of similar there. What's it, +1? We also have protons, which is a P or an H is used. We have a neutron as well. So these are again some very common symbols, and gamma, which has no symbol. So we talked about really balancing nuclear equations, and again, as we talked about, pretty straightforward. You just need to make sure all the mass numbers on the left-hand side of the arrow equal all the mass numbers on the right-hand side of the arrow, and all the atomic numbers on the left-hand side there equals all the atomic numbers on the right-hand side. Remember, sometimes things might be missing in an equation. So really the atomic number is usually the place where you want to start with that, because if you can find the missing atomic number, you can pretty much use the periodic table and figure out what element we're talking about. And then obviously you can figure out the mass number. We do not have, as we talked about, sort of conservation of the elements, because in a nuclear reaction, it's all about really converting things like protons to neutrons, neutrons to protons. So it's all about in that nucleus, and the protons is basically what determines what element we're dealing with. So since we're kind of changing those things in these type of reactions, we typically don't have the conservation of those elements. That's also why in sort of chemical reactions, we do have the conservation of those elements, because all we're playing with is basically electrons breaking bonds and making bonds. We don't do anything with the nucleus, which means the number of protons stay the same along the way, and we keep the same elements as we go through it. Any questions on that stuff there? All right, so continuing on here. The next thing we're going to talk about is what is referred to as stability. And one way that we look at stability is what is referred to as the N to Z ratio, or really your neutron to proton ratio. And the number of neutrons to protons, if it actually is too high, it will be considered sort of unstable. And what will happen in that case is it will kind of go through some radioactive decay in an effort to bring itself back to more of a stable situation. It may not hit perfectly stable, but it will kind of move itself back. As we will see, there is sort of a strip, if you will, which is sometimes referred to as the valley of stability. Um, And in terms of the stability, that's sort of a good N to Z ratio kind of falls within this line. And you may find yourself when you calculate it either too high or too low in terms of it. And if you're too high, what will happen is some neutrons will be converted through a beta decay. So if you calculate the N to Z ratio and it's considered too high, that element there or isotope will go through a beta decay in an effort to bring down the ratio, and that should move them closer to this sort of valley of stability, or sometimes people call it the belt of stability. And opposite is true. If your ratio is too low, we actually convert some protons into neutrons. And what we end up happening here is we're going to kind of bring our ratio up. And there's actually two ways that you could kind of do that. You could do either a positron emission or an electron capture. You could also do alpha decay, but is not as efficient. So for us, we will stick to just these two modes here, positron emission or electron capture, and that will bring the ratio up. Now you may be saying to yourself, why do you have maybe two options on that? And if we just look back at, I think we did one here. We did that one. It was beryllium 7. That was the one we were looking at. So the one we finished up on last time was beryllium-7, and it went through a positron. No, sorry, it went through electron capture. I'm sorry. And when we wrote our balanced equation, again, a reminder, we had our beryllium, which has a mass number of 7, atomic number there of 4 from the periodic table. Electron capture means that it captured an electron, so it's going to be on the reactant side. And again, when we add up our atomic numbers, that gave us our 3, which gave us our lithium, and our 7 on top. So that was an electron capture. If we started with the exact same thing, but instead did a positron emission, we will actually end up with the same thing. So in this case, we start with our 7, 4 in beryllium. Emission means the particles on the product side. So you got your positron emission, and that would mean that you would still need 7, 3, and lithium. So you have two options here. They both will end up with the same product that will be produced if you have to go through this route. So that's why, again, you have kind of those two options. They kind of end up the same at the end in terms of what is made. So either one will get you there. Any questions on that there? So let's talk a little bit about how do we know sort of what's a good ratio, what's a bad ratio. And like I said before, the valley stability is also sometimes referred to as the belt of stability. And again, that's sort of a nice stable sort of arrangement of neutrons and protons. And it is sort of based on atomic numbers. So if you have an atomic number that runs from 1 through 20, a stable ratio is going to be 1. If your atomic number runs from 20 to 40, your stable ratio is going to be 1.25. And if you go from 40 to 80, you're looking at 1.5 in terms of your stable ratio. As we talked about before, anything over 84 there is going to be radioactive, so they're not going to be stable to begin with. Now, there is some sort of gray areas, as you can kind of see, in terms of where one cutoff stops and the next one kind of starts. And again, here this stops at 40, and then this one starts at 40. So there is sort of a gray area if you kind of find yourself in the like that number and stuff like that. So to make it easy for us, we're just going to use this as pretty hard cutoff. So either it is 1 or it is 1.25 or it is 1.5. And if it's not, it's either higher or lower. So we're going to try to cut out the gray areas. I will try not to give you one, obviously, that would be in that sort of gray area. But if you do, sometimes you'll find they'll go, well, it's still okay because it's kind of in that transition area between sort of elements and stuff like that. So we'll go kind of with the hard cutoffs on these. And either it is that number or again, it's too high or too low. All right, so let's take a look here. Let's take a look at magnesium 22. And magnesium 22 is the mass number. Once again, here we could go to the periodic table and grab our atomic number 12. We're looking for our N to Z ratio here. And our N to Z ratio is number of neutrons. So number of neutrons is our mass number, which is 22, minus our atomic number, right? So our A minus our Z, right? And that's going to give me, I believe, 10 if I did the math there. And that means that my N to Z ratio would be 10 divided by 12. And that's going to get me a ratio here of, looks like 0.833. Now, the atomic number here for magnesium is 12, which falls in the 1 through 20 range of atomic numbers, where an acceptable ratio is 1. In this case, we can see that our ratio here is too low. So we're like on this side, not really way over there, but we're kind of below the belt of stability. So we want to kind of bring it upwards. So as we just saw there a second ago, if we take a look, right, if we have something that is too low, it can do one of two things, positron emission or electron capture. And again, you can choose either one if you're going to write what's going to happen here. So if we take our 2212 magnesium, we do an electron capture, which puts the electron on the reactant side. That's going to give us an 1122 and a sodium. You also could do, once again, that positron emission, which means the positron particle would be on the product side, and that's also going to give us an 1122, and sodium would be formed. Now, we could take a look here and see, did we actually sort of achieve what we were looking to do? If we take a look at sodium 22 and 11, the number of neutrons in this case would be 22 minus 11, which is 11. And obviously the number of protons is 11. So when we do our N to Z ratio for this guy, that's 11 over 11, which is a ratio of 1, which definitely moved us actually perfect now at this case into that. By the way, it will not always end up perfect. You will not always move into like a perfect ratio or something like that, but you definitely should move closer in the right direction towards that perfect ratio. If you're asked like what is produced, you don't have to keep doing it until you find something that's perfect. So just like the first sodium here would be what would be produced. Questions on that there? Okay. Why don't you try one here then? Let's do Krypton 85. Okay, let's take a look. So again, Krypton 85 is the mass number. You get the atomic number there from the periodic table. 36, going to look at the N to Z ratio here. So our neutron is going to be our mass number, 85 minus 36 there. That's going to get us, we got there 49, looks like. And that means we've got 49 divided by 36 for our ratio. And that's going to get us a 1.36 in terms of our ratio. This is an atomic number of 36, which means it puts it in the 20 to 40 category, where an acceptable stable ratio is 1.25. This obviously comparison is too high. And because it's too high, that means we're looking at a beta decay here that's going to happen to, again, bring the ratio down. And if we wrote our equation here, we got 85 krypton 36. Beta decay means a beta particle is going to be emitted, and that's on the product side. Remember, though, that is a negative one, which means we actually will need go up one in terms of our atomic number, which would be 37. We go to our handy dandy periodic table here, and 37 is RB. Up on top, we have 85 and 0, so 85 there. Again, if we take a look at sort of what we formed here, the number of neutrons in our new guy, 85 minus 37, is going to get us here 48 neutrons. Again, converting some neutrons here. And that will take 48 divided by 37. And in this case, we end up with about a 1.3. Again, not perfect, but definitely moving down towards the ratio. So again, like I said, you won't always get a perfect ratio as a result of that decay. Any questions on that there? Okay. And hopefully they agree. Let's see. That's good. All right. Now, that is probably a very good way to look at stability and a very common way to sort of look at stability. But there are other sort of factors that we sometimes look at when we're looking at stability of radioactive or just isotopes in general. Most stable nuclei will have an even number of protons and neutrons. So only a few will have odd number of protons and neutrons. And you can see that from this table here. Kind of your best sort of arrangement, if you will, as obviously these are protons and neutrons. As you can see on the even situation, there's 157 sort of nice stable isotopes with those. And again, that's your best option. Your next best option is even protons, odd neutrons. You got 53. Not too far off from that is odd protons and even neutrons. So just having something even in there is usually not too bad. Worst situation in terms of stability is odd and odd, and there's only about 5 nuclei that have that sort of arrangement. So that's sort of your worst one. So if you're just kind of quickly trying to figure out sort of stability, again, if you got even sort of protons and neutrons, that's going to be probably a pretty good indicator. If you got odd of both of those, bad indicator of stability. And you've got at least one even thing in there, either protons or neutrons. It's not the greatest, but it's not the worst sort of situation. In addition, the total number of nucleons, and nucleons is something that is mentioned a lot in nuclear chemistry. Nucleons is a fancy way of saying basically your mass number is what's inside the nucleus. So that's your protons and your neutrons, is basically what a nucleon is. If they add up to magic numbers, then it's stable. It's kind of like stability and bonding when everybody tries to get to like the noble gas configuration in terms of their electrons. So if these sort of guys, protons and neutrons, add up to these sort of numbers, then you sort of get a pretty good stability. They're most stable when either neutrons or protons are 2, 8, 20, 28, 50, 82, and your mega number is 126 there in terms of neutrons. So those are just some other ways to look at stability. Probably the most often you look at stability or ways would be the entity ratio, or kind of positive, even, or odd type of guys. And we'll take a look at another way to look at stability a little bit later on. Now, a decay series is a series of radioactive decay reactions where basically start with a parent nuclei, as we talked about before, and they create some daughter nuclei. And it's a series of reactions where they continue to sort of go through a decay process until they kind of hit something that's stable, and they kind of will stop at that point. Usually fairly long back-to-back sort of emission sort of things that happen. And there's a couple of ways that you could kind of figure out what you would get. Obviously, you can just do it each reaction based on, like we did our balancing nuclear reactions, and just write a nuclear equation for each step along the way. If you're dealing with alpha and beta decays, you actually can sort of shorthand it if you're only interested in sort of what's at the end. For every alpha decay, you minus 4 from the mass number, and you take 2 from the atomic number. And for every beta decay, you add 1 to the atomic number. Add 1 to the atomic number. So if you have something that's just going through alpha and beta decays, you just want to kind of figure out, what you get at the end. You can just kind of add them up and kind of go through that. So for example, if we looked at, you say, uranium 238, and let's just say it went through, I'll just make this up, a short little decay, alpha, alpha, beta, alpha, beta, and it went through sort of these 5 little decay processes here. So one way that you could kind of go through it is just simply just do it like balancing nuclear equations, which is not bad. And that means that you would start with uranium 238. You would go to the periodic table, obviously, and look up uranium's atomic number, which is 92. So the first decay process here is going to be an alpha decay, which means you would have the alpha particle on the product side, and you would just find your normal guy that would produce, which is 90, and looks like 234. Go to periodic table, number 90 is TH. Now, what you do is whatever is formed in that first step is now your starting guy in the second step. So you carry that guy down, and now that guy is going to go through an alpha decay, which will kind of do similar thing. Our new sort of atomic number is going to be 90 minus 2, which is 88, and 234 minus 4, which is 230. Again, you go to the periodic table, find number 88 somewhere there, RA. And now this guy will be your starting on the next step in this decay series. And that guy is going to go through a beta decay, which means the beta particle will be on the product side. Remember, with that -1, we got to bounce up 1 in terms of our atomic number to 89, gives us 230. And again, going to periodic table, finding 89, a little AC. Then this guy goes the next step. And that guy is going to go through an alpha decay. And now we're going to end up at 87 and 226, I believe. And 87, there is little francium. And lastly, this guy will come down here to 26, 87. Francium will go through a beta decay. Francium will go through a beta decay, which means the beta particle will be on the product side. And now this guy is going to go through a beta decay, which means the beta particle will be on the product side. And now this guy is going to go through a beta decay, which means the beta particle will be on the product side. And now this guy is going to go through a beta decay, which means the beta particle will be on the product side. And now this guy is going to go through a beta decay, which means the beta particle will be on the product side. And now this guy is going to go through a beta decay, which means the beta particle will be on the product side. And now this guy is going to go through a beta decay, which means the beta particle will be on the product side. And now this guy is going to go through a beta decay, which means the beta particle will be on the product side. And now this guy is going to go through a beta decay, which means the beta particle will be on the product side. And now this guy is going to go through a beta decay, which means the beta particle will be on the product side. And And again, with the negative, we got to bounce up one there to 88, 226, and lastly, 88 back to RA. So if you have a decay series here, basically just continue writing and balancing nuclear equations like we did earlier. Just whatever your product is in the first step becomes your starting in the second, and just kind of keeps balancing. Now, if you were just maybe interested in what you get at the end and not really each individual step, you could kind of do the little math down here. You could start with your 238 and 92. And in this case, we had 3 alpha particles. So we had 3 alpha decays, which means we're going to go -4, -4, -4, -2, -2, -2, right, for our alphas. And then obviously here we had 2 beta decays, which means on the bottom there we're going to add 1 back. So obviously here that's 238 -4, 234, 230, and obviously down to our, what did I say there, 226. 92 less 2 is 90, less 2 more is 88, less 2 more is 86, add 2 back to 88, and there it is. Yeah, there's our final product right there in terms of that. So again, if you're just kind of looking for the end product and they're all alpha and beta decays, you can kind of just do it mathematically and figure out what you get. Or again, you could kind of go stepwise through each case in case you need each individual sort of product. Any questions out there? Obviously, the idea behind this is it will continue on until it hits something that is stable. Obviously, what I just made up is probably not stable, but it would go through, obviously, always till it hits something. All right. And taking a look at specifically uranium-238, it actually can go through 2 different sort of pathways, but they both end up all the way down here at lead with 206, which is again a stable version. So you can see there's a lot of decay processes to get uranium all the way down to something that is stable. All right, next we're going to talk about kinetics of radioactive decay, which is everybody's favorite topic, kinetics. The good news is it's the same kinetics that we did earlier in the season here. So all radioactive decay follow first order kinetics, and as professional chemistry students you remember first order kinetics has a rate constant of reciprocal seconds or some type of unit of time, 1/minutes, 1/hours, whatever it may be. It has the integrated rate law, right? The natural log of A is equal to the natural log of A naught minus KT, and our favorite half-life equation ever, the natural log of 2 divided by the rate constant here. So my recommendation is, since you already know these are really the same formulas that you use for radioactive decay here. Uh, Although it is radioactive decay, they sometimes like to use different sort of symbols and some different words, but it's really the same formulas that we used previously. So obviously you can see here, instead of A, they will use N to represent nuclides that are going under radioactive decay, but it's basically the same thing. It's your final concentration, your initial concentration. Instead of K, which we call this usually in normal kinetics, the rate constant, this is what is referred to as the decay constant. So same idea. And also sometimes in nuclear chemistry, instead of K, they will actually use lambda as the decay constant. So you'll sometimes see lambda used as the decay constant. It's actually not wavelength in this case. If it's in this context, sometimes we'll use lambda instead of K. I think your book will use K still, but some books will use lambda in place of that. Again, the difference though is, and by the way, this is our still same graph that we normally see, natural log of A versus time, giving us that linear graph, right? Where the slope is equal to minus the decay constant in this case. So it's all the same first order kinetics that we've done before. The main difference is what we did when we kind of dealt with kinetics is we oftentimes use molarity as like our initial molarity, final molarity, and stuff like that. But really, in nuclear chemistry, these could really be any unit. So they could be grams, they could be milligrams. They could also very commonly, as we'll see in some examples, be like rates of radioactive decay, how many counts per minute or something. So they can really be any type of unit, but again, it kind of works the same way, kind of beginning and ending concentrations, units, and basically everything else kind of works the same. Also, I would say probably a little bit more common than what we saw with kinetics is you'll oftentimes have to use both of these equations together. So very commonly, because it's dealing with radioactive decay, they very often like to give you the half-life information and not necessarily the decay constant. So a lot of times you'll have to use the half-life information to figure out the decay constant and then use your integrated rate law to figure out, what you're really looking for, either a concentration or a time or something like that. So I would say you kind of use both of those formulas together a lot more than maybe we did in regular kinetics. There's our old school pictures we like. And those are our typical first order graphs, again, using N here. And as I mentioned before, that is the decay constant. And some books will, again, use lambda for that rather than K, but some books will also use K as well. As we know, as we talked about in terms of half-life obviously is the time it takes for half of whatever you started with to sort of go away. And in terms of radioactive sort of nuclei, that could be anywhere from seconds to years to days to weeks and stuff like that. So you can see uranium-238, which uranium, for example, is used in like nuclear power plants and fission type reactions, has a half-life of 4.5 times 10 to the 9 years, which means none of us will be here for any half-life of it probably. So it's a very, very long time. But you can see something like this here, thorium 219, has a very, very short half-life. That thing will be dead pretty quickly, right? It will go over a lot of half-lives very, very fast. And obviously, as we'll talk about a little bit at the end of the chapter, if you're doing something in, say, medicine or something like that, you would obviously want to use something that is a smaller half-life, right? Quicker half-life than obviously other things. You wouldn't want your years and half-life because your follow-up appointments would be very long down the road. So let's take a look here at an example. If you have 1.35 milligrams of plutonium-236, calculate the mass that will remain after 5 years. I think the half-life is given to you here somewhere. Where did it go? It disappeared. Let me see if I can find it here. Pretty close, 2.86 years now. All right, so the half-life here is 2.86 years for plutonium. All right, so why don't you give it a go there and see how much should be left over after 5 years? Again, it's basically first order. Okay, so let's take a look. So again, you could always be safe if it's something to do with radioactivity. In terms of which ones you should use, it's always going to be first order. So I'm just going to use our normal sort of symbols for it. If you like the fancy nuclear ones, you can if you use those. Now, in this particular case, we have kind of our initial concentration here of 1.35 milligrams. We want to know how much is going to be left over at the end, and the time is 5 years here. So we do have kind of time. We have that. We were looking for this. We are missing the decay constant here, and that is where the half-life was given to you for. We could use our half-life equation here once again to get the decay constant. So if we do that, our decay constant should equal the natural log of 2 divided by our half-life. That gives us a natural log of 2 divided by 2.86 years. And that's going to give us here natural log of 2 divided by 2.86 years. Can give us 0.242, we'll call it 4. These are reciprocal years, so that's just like a decay constant or a rate constant, 1 over some type of unit of time. We also always want to remember, right, when we're using this equation, these two guys here need to be in the same time unit. In this case, they are times in 5 years, and this is in years, so we're all good there. So we're good to put in our natural log of what we're looking for. It's going to be the natural log of our 1.35 minus our k that we just got there, reciprocal years times our 5 years. Again, our years are going to cancel, and we clean up the right-hand side, natural log of 1.35 minus 0.242 times 5. It's going to give us the natural log of A is equal to minus 0.911895. We're going to E both sides there. Going to give us our final concentration of, looks like 0.402. These would be milligrams, just like the original unit is. It does make sense because it's decaying, so our final should be less than what we started with, right? So obviously, if you got more, something not so right there along the way. Any questions on that one there? We'll throw back to the beginning here. There you go. All right, let's take a look at a couple more here. Maybe let's try radon. 222 causes lung cancer. If there is 10.24 grams of it in the house today, how much will be there in 5.4 weeks? The half-life of radon is 3.8 days. So again, we already know sort of which kinetics we're going to use. So we'll pop our equations in here. All right, so in this case, we have our initial concentration of 10.24 grams. We have 5.4 weeks, and we want to know again how much is going to be there at the end. And we have a half-life given to us here of 3.8 days. So once again, we're going to use our half-life equation here to get our decay constant. We do have some different units here in terms of time. At some point, you do need to sort of get them into the same unit before they go into there. Otherwise, again, you're going to be off. So it doesn't really matter which one you want to do, but I'll turn that into weeks here. Why not? So I'll take my 3.8 days, and I think there's 7 days, they say, in a week. And that's going to get me for my half-life in terms of weeks here, 0.54286 weeks. You obviously could also convert this into days and just leave that one obviously as days as well. So solving for our rate constant here, natural log of 2 divided by our half-life, which I've now converted into weeks. 86 weeks. That's going to get us here, natural log of 2 divided by 0.54286. Looks like 1.277. And again, this can be reciprocal weeks. And now we can put into here our natural log of what we're looking for, natural log of our initial there, 10.24 minus our 1.277 weeks times our 5.4 weeks at this point. Again, the weeks are now going to cancel. All good. Clean up the right-hand side. Natural log of 10.24 minus 1.277 times 5.4. Going to get us here a natural log of A is equal to minus 4.569. Going to E there. And that is going to get us, oops, not that, hit the right button maybe. There you go. Well, it looks like maybe 0.0101, we'll call it. And these would be grams in this case here. Any questions on that there? All right, so again, it's just the normal sort of thing we're using this. Got to watch units along the way. All right. Now, we could also use radioactive decay and really kinetics to figure out, how old something is through a couple different ways. You could do carbon dating, which is obviously how much carbon there's going to decompose into, say, nitrogen in this case. Carbon-14 has a half-life of 5730 years. You could also do uranium dating, which again will decay into lead. And really the difference between how much lead is left over, you can kind of figure it out as well. And uranium there, 4.51 times 10 to the 9 years in terms of that. So let's take a look at one here and just sort of walk through it here together. Let's take a look. The ancient skull gives 4.5. Now, this is, as I was mentioning before, when we're doing our kinetics, doesn't have to be nice clean units like we've seen before. This is a unit of radioactive decay, and that is disintegrations per minute per gram of carbon is the C. It is not Celsius, so it's actually per gram of carbon here. And again, that is a unit of radioactive decay. If a living organism gives us 15.3 disintegrations per minute per gram of carbon, if we want to know how old the skull is, the carbon parts here is important because it tells us We should roll with the half-life here of carbon, which is 5730. So again, that's a piece of information that may not necessarily be given to you, but 5730 is the half-life there of our carbon. Even though it's some crazy looking units there, it's still our first order kinetics that we're going to do here. In this case, though, we are looking for time, which is how old the thing is. We do have the initial and the final. Once again, here we're kind of missing our decay constant, so we will need to use that half-life to get us our decay constant. Now, our initial is, well, frankly, living would be initial, right? That's usually how it goes. So that's going to be our 15.3 disintegrations per minute per gram of carbon. And not so ancient there is going to be at the end is 4.5 disintegrations per minute per gram of carbon. Obviously, here we're going to use our half-life equation just like previously to get to our K. So our natural log of 2 divided by our half-life, which would be the natural log of 2 divided by 5730 years. In this case, we can leave it in years because it just means our time is going to be in years, which is fine, what we're looking for. That's going to get us here, the natural log of 2 divided by 5730. That's going to get us 0.000121 reciprocal years as our decay constant. Popping this in, we're going to go natural log of our final, which is 4.5, equals the natural log of our initial, which is 15.3, minus our constant we just calculated there in years, reciprocal years, 121 reciprocal years, and our t. So we're going to solve for t here. We're going to take the natural log of 4.5. We're going to subtract it from the natural log of 15.3. So basically going to subtract this to the other side. That's going to give us 0.57219 equals negative. I feel like maybe I hit the wrong button there. We'll try that again. Natural log of 4.5 minus the natural log. I probably did hit the wrong button. There we go. Natural log of 15.3. There we go. Negative. That is definitely the wrong button I hit on that thing. That did not look right. All right, let's try with the right button hitting would help. Negative 1.2238 equals our negative 0.000121 years in time. Obviously, now we're going to divide that to the other side. And the two negatives now should cancel each other out, which is good. And we're going to end up with this ancient skull is about 10,114 years old. And you could kind of clean it up to 10,100 years if you're looking at sig figs, like that. Any questions on that? So basically, just solving for time here, and you could obviously figure out how old something is. Any questions on that? All right, so why don't you try one here? Archaeologists have found dated civilization to 15,600 years ago. If a living sample gives 20 counts per minute per gram of carbon, what would be the number of counts per minute per gram of carbon in a grain of rice that is found on the site? Again, we're using carbon, so same half-life. Another sort of rate as our sort of concentration units, if you will. So natural log of A is equal to natural log of A naught minus KT. Here we have a living system, so that's going to be our initial at 20 counts per minute. We are looking for what it will be at the end. We have a time that's 15,600 years. And again, it's per gram of carbon here, which means we could use our same half-life sort of deal as last time. And again, we could also use the same result of that, which is obviously 5730. So I'm just going to grab our same sort of guy that we did previously, as we'll end up with the same decay constant there off of our 5730 half-life, which we need as well. So that was 0.000121 reciprocal years is our decay constant. Obviously, that would be solved from here the exact same way we did on the previous problem. And then we could actually just pop it in there, I think. So let's do that. Natural log of A is going to equal our natural log of 20 minus 0.000121 reciprocal years, and our time here, which was 15,600 years. Again, we're good in terms of our units. They're both going to cancel out correctly. That looks like it actually. Times 1560. We're going to take the natural log of 20, minus it by the rest of that there. And it looks like natural log of A equals 2.807. Going to take the E of both sides there, and E of both sides there. And we'll end up with, just make sure I got that right here. Shouldn't be hitting some wrong buttons here today. Let's try to go 1560. That looks good. All right, so we're going to E both sides, and looks like we end up with about 16.6 counts per minute per gram of carbon. Any questions on that there? So obviously you could use it here, and that way on the final exam you tell me how old your in and out double is when you get it there, and you found it in the parking lot. Any questions on that there? All right. Something not right here. What's not right here? Natural log of 20 minus. That's not right. I think I did 1560. That would be wrong. Banner day here on the calculator. There we go. Last day. Don't know how to use the calculator. It's just a bad sign. All right. So we'll just cut it out in post editing and it'll all be good. Nobody will see it. That's all right. So 3.03, which is nowhere near what I got there originally, per minute per gram of carbon. That looks better, maybe. All right. There you go. Hey, in my defense, I put a circle around that. Oh, I missed it right there. All right. There we go. Uh, All right, so next thing we're going to talk about is actually the energy that comes from fission. And fission, by the way, again, is the sort of, it can happen either you can kind of initiate it or it can happen spontaneously. But typically, fission is you have some type of unstable nucleus. It obviously goes through radioactive decay. It typically will create two new nucleuses. Will also oftentimes create a lot of neutrons. And more importantly, it will release a lot of energy in that process. And that is the energy that's used in a fission reaction, like I said before, in like a nuclear power plant or something like that. They use a fission type reaction. You could calculate the energy that's coming off of that using Einstein's equation equals mc squared. C being obviously the speed of light. We'll go with 3 times 10 to the 8 meters per second. And you definitely get a lot more energy being released from uranium in the fission reaction than you do in a traditional sort of exothermic reaction. You can see you get about 10 to the 13 joules of energy for every mole of uranium that goes through fission versus in the kind of really exothermic reaction, 10 to the 6 joules of energy. So you got a lot more energy per mole that comes out in that fission type reaction. Now, when that process occurs, there is something known as the mass defect. So when a nucleus forms, there is a difference between the mass of the separate nucleons, which again are your protons and neutrons, uh, and really the mass of the isotope itself. And that slight difference of mass is going to be converted into energy via Einstein's equation. You could do it. And that difference in mass is what's known as the mass defect. So when we look at Einstein's equation in this application, that is like the mass defect is sort of what would go into that spot of it right there. Now, here are some conversions which can allow you 1 megaelectron volt is 1.602 times 10 to the minus 13 joules. And 1 AMU of mass defect is equal to 931.5 megaelectron volts. So, two very common units of binding energy or nuclear binding energy are joules per nucleon or mega electron volts per nucleon. So those are two sort of common sort of units that are used for binding energy. You could actually use binding energy as a measure of stability. So the greater the binding energy per nucleon is, the more stable something is. So that's another way that you can look at stability is by looking at the binding energy per nucleon. So these two here can be used to sort of bypass Einstein's equation, or you can use Einstein's equation to sort of calculate the binding energy. So let's take a look at an example of that here. And we have, say, fluorine, and fluorine has a fluorine 19. So fluorine 19 would have, in terms of the number of neutrons, 19 minus our 9, and that is going to give us 10 in terms of our neutrons. Obviously, the number of protons here is 9 in this case. So we could actually use the atomic mass of a proton. So a proton's atomic mass in AMU is 1.007825 AMU. And a neutron's atomic mass there in AMU is 1.008665. As you might remember, the neutron is the heaviest of the three particles, just barely inching out the proton. So we could calculate the mass defect, and you could calculate the mass defect by taking the number of protons and the number of neutrons and basically adding them up together with their masses. So we have 10 times our number of neutrons, 1.008665 AMU, and that's for our neutrons, plus our 9 protons at 1.007825 AMU each. And then subtract it, I'll just go below it a little bit, from the isotope's atomic mass, which is 18.9984 AMU. And that would typically be given to you in a problem, sort of the atomic mass of the isotope. And if you do that, that is going to give us our mass defect, which is here, 10 times 1.008665. Oh boy. We'll hope for the best here as I punch these in. Let's see, there we go. And we're going to subtract an 18.9984. There, my calculator is ready on vacation. 675 AMU. So that is the mass defect. That's the amount of mass that's going to be converted into energy via this process. So there are two sort of outways that you could kind of calculate the binding energy at this point. You can use Einstein's equations. So if we use E is equal to mc squared, that is going to be the mass defect we're going to put in there. We're going to times it by 3 times 10 to the 8 meters per second squared. And that's going to get us here 0.15. Actually, we'll just use that times 3 to the 8 squared. We're going to go 1.43 times 10 to the 16. My units at this point are AMU, meters squared, seconds squared. And we can convert that into joules by taking a number that looks familiar, maybe 6.022 times 10 to the 26. Not 23, because 26 gives me kilograms and 23 gives me grams. Yeah, so Avogadro number to the 26 will get me to kilograms, and that will get me here 6.022 to the 26. That'll give me 2.37 times 10 to the minus 11. My units are now going to be kilograms, meter squared, second squared, which you hopefully will recognize as a joule. Yeah, so that is equal to a joule. Yeah, so all that is equal to a joule. Yeah. Now we can get this per nucleon by dividing this by the number of nucleons, and the number of nucleons are essentially the mass number, so that would be 19 nucleons. We'll take that number divided by 19, and that'll get us a 1.2, we'll call it 5, times 10 to the minus 12 joules per nucleon. So any questions on that there? Now, if you wanted to convert that into mega electron volts per nucleon, you can use, actually, I'll borrow this page here and we'll take a look at it here. We can take our 1.25 times 10 to the minus 12 joules per nucleon. And we could also just use our conversion here between joules and mega electron volts. And we'll go 1.602 times 10 to the minus 13 joules per 1 mega electron volt. We'll take 1.602 to the minus 13. Going to give us something like 7.791 mega electron volts per nucleon. And that is obviously to the common units that are used for binding energy per nucleon. So that is one way you could do it. It's obviously Einstein's equation. Look, if you want to kind of avoid Einstein's equation altogether, you could just pick up with our mass defect, which we calculated earlier as, where did it go there? 0.1587 AMU. And you can use this bottom conversion here. 1 AMU is mega electron volts, 931.5. And we'll take our number, times it by 931.5, will give us 147.8 mega electron volts divided by 19 nucleons. And essentially, with rounding, gets you pretty close to the number above, 7.78 mega electron volts per nucleon. So you could go that way as well and not use Einstein's equation. You could then, if you wanted joules, obviously use the conversion below and convert it to joules. So it's your call of whichever way you want to go on that. And it may depend on the units that you're looking for. Any questions on that there? All right, so why don't you try here? Actually, let's take a look at one here. Again, this is a graph showing the stability, and as I mentioned before, you could use it as a measure of stability. So as the binding energy per nucleon increases, so does the nuclear stability. Right there, 56, iron 56, kind of your highest relationship there, most stable, as you can see also on here as well. Things that fall kind of after that will go either through fusion or fission to try to get things more stable. So why don't you try one here? Calculate the mass defect and binding energy per nucleon. And let's get you those numbers we used previously. Oh, we're on there. There it is. So neutron 1.008665 AMU, and a proton was 1.007825 AMU. All right, good to go. Obviously, carbon is number 6 on the periodic table. Okay, let's take a look here. So we'll go our number of neutrons should be 16 minus 6, which would be 10. And obviously our number of protons here should be 6. So we'll calculate our mass defect first. So our mass defect going to be our 10 times our neutron, 1.008665. We're going to add that to 6 times our proton mass. Then we're going to subtract that from the isotope's mass there of 16.014701. And that's going to get us here 10 times 1.008665. 0.008665. There we go. Plus 6 times 1.007825 minus 16.014701. Going to hit us 0.1189 AMU as our mass defect. Again, in this case, we are looking for mega electron volts, so we could probably just go with 0.1189 AMU. If you don't want to use Einstein's equation, you can use that conversion of 931.5 mega electron volts per AMU. And if we take that and times it by that, can give us about 110.8 mega electron volts. We could divide it by our nucleons, which is really our mass number, which is 16 in this case. And that will get us something like 6.922 mega electron volts per nucleon. Again, if we happen to be interested in joules, we could also get to that from here as well by using our conversion there. That then 1 mega electron volt, there's 1.602 times 10 to the minus 13 joules. And that would get us times 1.602 to the minus 13. Get something like 1.1 times 10 to the minus 12 joules per nucleon if we were looking for in joules. If you went Einstein's approach, you would end up in joules and then have to maybe convert out over to mega electron volts. This again is a measure of stability. If we look at this as a 6.922 versus our fluorine here that we got 7.79. So based on binding energy per nucleon, fluorine should be more stable than obviously the one we just looked at there, which I forget what it was now. But iron, thank you. Carbon 16. Yep. Any questions on that there? All right, we're